Hey everyone, and welcome back. Today, we're going to dive into a corner of mathematics that's a little weird, a little wonderful, the world of complex numbers. Now, they might sound super intimidating, but you'll see they're actually the secret key to solving problems that for the longest time seemed completely impossible. So let's jump right in. It all starts with a simple-looking puzzle like this one. X squared plus 9 equals 0. Now, if you try to solve it the old-fashioned way, you hit a wall, and you hit it fast. You get x squared equals -9. And you stop and think, wait a minute, what number, when you multiply it by itself, gives you a negative number? With the numbers we use every day, there isn't one. It's impossible. So here's our game plan for this explainer. First, we'll look at exactly why this problem is such a brick wall. Then, we'll introduce the brilliant, kind of crazy, imaginary key that lets us smash right through it. From there, we'll learn how to build a whole new type of number, see what these numbers actually look like, and then finally, we'll circle all the way back to unlock the solution to that first problem. First up, let's talk about hitting that wall with the numbers we all know and love, the real numbers. Okay, so let's think back to math class. There's this one fundamental rule that gets drilled into our heads. You take any real number, it doesn't matter if it's positive, negative, a fraction, whatever, and when you square it, the result is always 0 or positive, right? A positive times a positive is positive, and a negative times a negative is also positive. And that rule is precisely why our little equation, x squared equals -9, is a total dead end. There is literally no number on that familiar number line that can make this equation true. As far as real numbers are concerned, the system is broken. There's no solution here. So when you're faced with a wall like that, what do? Well, if you're a mathematician, you do something kind of bold. You get creative. You ask, what if the rules are the problem? What if we just invented a new rule? And this is it. This is the big idea. This is the key that unlocks everything. They defined a new number called I, the imaginary unit, and its whole purpose in life is to do one specific thing. When you square it, you get -1. It breaks that old rule on purpose, and by doing that, it blows the doors open to a whole new mathematical universe. Now, I know what you're thinking. Imaginary. It sounds, well, made up. But don't get too hung up on the name. As the source material points out so well, can you physically hold a 3 or a pi? Nope. All numbers are just abstract ideas we've created to describe the world. This is just one more incredibly useful one. Okay, so we have our powerful new key, I. Now the fun really begins, because we can start to build a whole new category of numbers with it. And this is what it looks like. This is the standard form for a complex number. I know, it looks a little weird at first, but it's actually just a simple combination of two parts we already know. A regular real number, A, and another real number, B, that's just being multiplied by our new friend, I. And this breaks it down perfectly. Every single complex number has a real part, that's the A, and an imaginary part, that's the B, the number that's tagging along with I. That's really all it is. It's a hybrid number, part real and part imaginary, living together. And you know what's great? Working with them is super intuitive. If you want to add or subtract two complex numbers, you just treat it like a simple algebra problem. You combine the real parts together, and then you combine the imaginary parts together. It's just like combining like terms. Easy. Okay, so that's the algebra. But what do these things actually look like? I mean, can you even picture a number that's part real and part imaginary? Well, it turns out you can. You can actually map them out on a 2D plane. This is called an Argand diagram. Think of a normal graph, but instead of an x and a y axis, you have a horizontal real axis and a vertical imaginary axis. So a number like x plus iy just becomes the point xy on this map. All of a sudden, these abstract numbers become real, concrete points you can actually see and point to. Now here's a really neat and important idea, the complex conjugate. All you do to find it is you flip the sign of the imaginary part, and look what happens on the diagram. It creates a perfect mirror image, a reflection right across that horizontal real axis. This is going to be super useful in just a minute, trust me. This visual approach opens up all sorts of cool ways to think about these numbers. For example, you can picture each complex number as an arrow, a vector, drawn from the center of the graph out to its point. And any arrow, right, has two properties. It has a length, which in this world we call the modulus, and it has a direction, or an angle, which we call the argument.
All right, we've got the theory, we've got the algebra, we can even visualize them now. It's time. Let's bring it all together and go back to that problem from the very beginning.
Here it is again, our old friend, the seemingly impossible equation. But now we've got a secret weapon. Okay, let's do it. First, we get x squared by itself, so x squared equals -9. Now we take the square root of both sides. And instead of getting stuck, we can cleverly rewrite the square root of -9 as the square root of 9 times the square root of -1. Well, we know the square root of 9 is 3, and we defined the square root of -1 as our new number I. So the solution is just plus or minus 3i. And just like that, problem solved. And this isn't just a trick for simple problems. It's an absolutely essential tool for solving all sorts of quadratic equations. Take this one. If you plug these numbers into the good old quadratic formula, that bit under the square root sign, the discriminant, it ends up being negative. In the past, that's where we would have thrown up our hands and said, no real solution. But with our new tool, we can finish the job. And bam, there's the solution. And hey, notice anything familiar? The answers are 2 plus the square root of 3 times I and 2 minus the square root of 3 times I. They're a pair, a complex number and its conjugate, that mirror image we just saw. It's no coincidence. These solutions often show up in these neat pairs. And this brings us to one last kind of mind-bending thought to leave you with. We had to literally invent this imaginary unit just to solve problems in pure mathematics. But it turns out these very same numbers are absolutely essential for describing very real things in the physical world. We're talking everything from quantum mechanics to electrical engineering. So it really makes you wonder, right? If these so-called imaginary numbers are so fundamental to describing reality, how imaginary are they really?